Hello everyone, welcome back. So for today, what we're going to do is we're going to be going over the idea of robotic logic. In particular, how robots think and go through instructions, and in the same way, how do computers do the same thing. So we're going to be getting into some of the ideas behind coding itself, but as for today, we're not going to do any coding. All we're going to be doing is learning about the robotic logic, how that matters, and the different levels of computer programming that have been out there over the years itself. And then in the near future, we're going to tie into what that means as far as coding goes. So when we start off right now, one of the things we have to understand is what the definition of a computer actually is. So we know that computers are general purpose, which means they can be used for a variety of different circumstances. They're programmable, so we can change them up, all right, to fit our needs. They are information processors, so they're taking input information and output information, and they're having some way of dealing with that information as it comes in and as it comes out. Now, going a little further on, when we're looking at robots, a lot of times we're dealing with embedded computers or programmable computers itself. So an embedded computer essentially means they're machines with full computers on the inside, washing machines, airplanes, ATMs. Essentially, they're highly reliable and predictable computer programs because they're going to be used over and over and over again. They're embedded because we generally don't want to change the programming of an ATM too often. We do every now and then, but for the most part, we want that ATM to be highly reliable so it's not spitting out extra wads of cash. Or if you're the bank, that's what you want. If you're the consumer, you definitely want that to happen. If our computers interface with a physical mechanism, we typically will call these robotic devices. All right, not always the case. Sometimes there's only software, only robots out there, but for our intents and purposes and for what most people kind of discuss and will consider robots, they have to interact with the physical mechanism. So when we're looking at how computers and how robots solve problems, to solve a problem by a computer basically requires something that states what the problem is. So we need to first understand what we're trying to do with the computer itself through something called a problem statement. It's very similar to the engineering design process. You always have to know what you're trying to solve before you can actually start. Then you solve that problem using something called an algorithm. Essentially, it's just a set of instructions that goes about showing how you solve that problem itself. And then typically we use a computer or some other sort of machine to carry out those instructions itself. So these are the basics of how computers actually solve the problems. Now, I was talking about an algorithm earlier right there, and algorithms, what they are, they're just simply a clear sequence of instructions. All right, you're going from point A to point B, and these are the steps that you're taking as you go in between. Now, they are strictly defined sequences, which means you can't really jump out of line with these. Whatever it says to do, that's what the machine's going to do. It's going to be a strictly defined, strictly followed rule. All right. So they're well defined. On top of it, they have to be feasible. All right. They have to be something that the computer is actually going to be able to do itself. So a couple of examples of almost algorithms that aren't computer-like. To shampoo your hair, rinse, lather, repeat. That's an almost algorithm because that's just going to repeat over and over and over again. So essentially, you're just washing your hair forever and ever. But you see, it's a clear sequence of steps, something that you can actually physically do too. So it is a feasible thing. To set the time on a wash, push the button, set the hours, then the minutes. All right, pretty straightforward. To write the great American novel, all right, you guys are generally getting the idea. All right, an algorithm is simply a set of steps, a set of instructions that you need to take. Typically with humans, we don't really do well with algorithms, but machines do. Now, in understanding how computers talk and how they understand our instructions, we have to understand the difference between our natural languages and what artificial languages are themselves. Natural languages are spoken and written, stuff like English, Spanish, Portuguese, French, any stuff along those lines. They are created for human use, and they're meant for humans to communicate with one another. That was their purpose for creation. That's what they're used for, and that's what they've worked really well for the past, thousands and thousands of years. They do have flexible meanings, though. What that means is if I speak to you as I'm speaking now, if I don't say the words exactly the way they need to be said, which, as you guys have learned over the past month, that happens quite a bit. It actually happens quite a bit with humans itself, all right? We are not perfect beings that can spit out exactly the correct grammar, exactly the right spelling, any of that stuff. But we have that flexibility to be able to understand what that person's saying by deducing through that language itself, all right? Also, what this means is our languages are ambiguous in their use and meaning. What that means is if I said, make the bed, you aren't necessarily going to go out there and construct a bed from scratch with new lumber and stuff like that. You're probably going to go to your bedroom and you're going to pull the sheets and make your bed and, you know, make it all pretty, all that good stuff. All right, so if a robot heard that, they would literally construct the bed. All right. Now, artificial languages itself, they're utilized for machines. They work really well for this purpose. Stuff like C++, Java, Assembly, lots of other languages out there, Python. But the idea here is they're created for computers and machines. The computer or the machine is going to be able to take a look at that language. It's going to be able to understand what it is and translate it into something that it should do. All right. Now, as part of this, computers are mathematical in the way that they function. So their languages are going to be pretty mathematical as well. And what I mean by mathematical, this means is strict in meaning and interpretation. So what this means is that if you tell that computer to make the bed, it is literally constructing the bed. If you tell that computer to go forward, it's going to go forward. But if you never tell it to stop, it's just going to keep on going on and on and on. So you have to be really careful when you're talking with computers and programming themselves. It's one of those ideas that you've probably heard before. It's never the machine's fault, it's yours. Stuff like that. So there's no interpretation. It is or it is not. It's either a 1 or a 0. Now, what is computer science to actually understand what's going on here? Computer science is simply the study of computers, and in particular, the study of algorithmic processes, including their theory, analysis, design, efficiency, implementation, application. Essentially what we're saying here is we're trying to understand how computers think and trying to find the most efficient way to do that. The more efficient these algorithms and these rules that we create are, the faster our computers work, the less likelihood they have of crashing the programs, all right? And the less likelihood that you're going to throw your computer across the room because you're very angry that it's taking so slow, all right? So computer science is the way of going through and trying to understand all this. At its root, computer science has 2 specific fields that it's going to be dealing with. First one is mathematics, all right? A lot of people don't recognize, but computers and their computing power all came out of this idea of how can we think through problems in a mathematical solution. All right. Find some of the roots of computer science and mathematics with Alan Turing and the Turing machine back in the 1930s. Basically, back then, they were developing theories with paper and pencil about how to perform calculations by hand. The other major field is, go figure, you're in the class, engineering. Once we were able to actually create the mechanics in the machines, now we can actually use electronic circuitry to compute all these mathematic programs. All right. At the very beginning, when we're taking a look at physical computers, they literally were buttons and switches. You would turn on a switch, and that would be an input into the machine to do the calculations. Later on, I'll show you some of these old computers. They're really crazy and actually really cool to see operating. Now, in understanding how these machines think, we have to take a look at some of the 4 levels of computer coding. Now, these are the 4 main ones. There's a lot more that goes into this, but this kind of breaks it down so you guys can hopefully understand what's going on and how we're going to be coding and understanding these. Machine language is the very basic. That's the natural language of the computers. It's defined by their hardware design. So different types of hardware are going to have different types of machine languages. All right? Essentially, they're consisting of zeros and ones. So it is going to look like this. 1001, 1101, 1100, 1110. That right there is just 2 letters. It says hi. Now imagine taking that and putting together a whole entire computer. If you're looking at your computer, how it's operating right now, watching this, you're seeing trillions upon trillions of those ones and zeros going by all at once. It is incredible how much is going on through your computer. And to think how far we've gotten with these computers to be able to do that. As you can imagine, pretty cumbersome for humans to actually go through and code like this. That's why our early computers didn't really do too much. Nowadays, we can do extraordinary amounts because what we did is we developed languages a little bit beyond. The first one was this idea of an assembly language. In assembly, there's multiple different assembly languages out there. They used English-like abbreviations to represent basic operations. Mainly the idea here is to make it easier for humans to speak with the machines instead of having to type in 100111001, or not even type it. I guess back then you'd be pulling the switches up and down as you're going through. But in order to use these English-like abbreviations, the computers needed something to translate between the natural language, or human language, and the machine language. So basically going from assembly to the machine code. And so guess what? We have something called an assembler. An example of what these used to look like, if I wanted to load a program, I would just type in load and the program name. If I wanted to add two numbers, I would do 1 add 2. And just typing that in will actually add it up. Stuff like that. So very, very basic stuff that we're going through there. Obviously, it's a little better. I can tell you, though, that they taught me how to code in assembly when I was back in college, and it sucked. It's not the easiest way to go about. That's why we have something called a high-level language. These are languages that are similar to our everyday English and math that we're using all around us, and a little easier to deal with. You have single statements that will basically accomplish many tasks, and this is the code that we're going to be using a lot for our mini robots that we have. They still needed an assembler to translate it over into machine language, but we're using different languages like C++, C++, Java, Python, stuff like that. And you're going to see stuff like this. Int gross pay equals base pay plus overtime pay. So we're starting to see statements come through there, and we're starting to see something called a variable that makes life a lot easier too. And we're going to be going more into this later on. Last one is something called object-oriented programming, and we are going to get a little bit into this as well. You guys probably have seen this style before. Basically, an object is a physical block that you can kind of drag across a screen using a mouse or something along those lines, and these blocks will represent code. Reason people use it now is visually pleasing. It's good if you're not too far into, like if you're a person that's programming all the time, you're probably going to be using a high-level typewritten language. But if you're someone that does it every now and then, or a graphic designer, or working, say, with PLCs and electronic equipment in an industrial plant, you'll more than often be using object-oriented programming. It is a lot easier. And each object you have contains a lot of embedded code inside there that you can kind of like drag around and tell the machine what to do. This is stuff like EasyC, Visual Basic, like I said, PLCs, stuff along those lines. A lot of different options out there that I'll be showing you some of those later on this year too. Now, the way we go about in executing computer code itself is this kind of progress. We edit, so we write the code itself. We do something compile. What that's doing is it's using an assembler to create that machine code. Once we have that machine code, we load it onto the computer, and then we tell the computer, guess what? Run it. Execute that code. That way it can run the code and do what you want it to do. Now, when we're looking at robot logic, logic is defined as the specific use of reasoning itself. So what this means is it's a defined set of rules on how the machine's going to be running. All right? And this is where we're going to be getting into our task for the day. All right, in logic itself and in robotics, what this means is we're going to define the operations of the robot. Our first task is basically going to be having this robot drive through and move through different mazes. All right, so we're going to have to take a look at that and understand how to program it in specific ways. Now, I'm going to skip right through this right now because we're not doing VEX. But when we start dealing with the idea of sensors and input, we're going to have the sensors sense any sort of event, process what's being done through the program, and then act on it. This is essentially what we as humans do. Like right now, you're listening and you're watching this, you're processing in your brain, and you're acting on it by either asking questions or answering just the Edpuzzle itself. All right, same way kind of a robot goes through as well. Now, in robotic instruction, we're going to be dealing a lot with robotic logic. This means that computers and robots follow those rules very literally. Tell a robot to go forward, and it will. It just will never stop until you tell it to. So, what we're going to be doing is we're looking at these flowcharts. Now, a flowchart is essentially a representation of our algorithm, our robotic logic that we're going to be doing. They're going to follow a specific order of operation that includes stuff like loops and decisions. So right here you can see this is a program for having a person walk forward. First step, they're going to walk forward 5 steps. The question, is the wall in front of them? If it's no, they're going to keep on walking, and they repeat again 5 steps. So that's a decision right there. As soon as they see there's a wall in front, where it replies yes, then they want that person to stop. Turn left 90 degrees, walk forward 5 steps, and repeat the process over again. Now, these flowcharts that we go through are basically the building blocks of how our robots work, how computers work. It makes it a much easier way to take a look at what you need to do and design out the program. You can imagine if you're just going through all the text at first and trying to put it out that way, it's like the same thing as trying to build a house without having the plans for how to build the house, all right? Without having the dimensions and what you need there. Our flowcharts, all right, our algorithms right here are going to be the ones that drive through what we need to do. And you'll notice when we use our flowcharts, we have different symbols that we use as well. For the most part, we're going to be using mainly this oval, rectangles, and diamonds, as well as the flow lines. We're not going to have too much of these input operations that we're going to be dealing with right now. Oval is always going to be the beginning or the end of a program. All right, the lines always define what the next step is. So as soon as it's done executing, all right, that process, it goes on to the next step. Rectangle is a process to be carried out. So right here you can see this is our process, walk forward 5 steps. As soon as it's done operating that process, it goes on to the next one following the arrows. The diamonds are going to be decisions. All right, these are going to be something like our if, then, else statements that we may be talking about later on. But basically, they're going to be asking a question. They're either going to reply yes or no. There's only 2 answers to it, yes or no. It either meets that requirement or it doesn't. So in this case, are you at the wall? We have no, it goes back. Yes, it goes forward. All right. So what your task is going to be for today, typically we do this in the classroom. We'd have a maze set up and you'd be writing instructions for other people in the class itself. But because it's a little different, we're going to be doing this at your guys' homes. So what you're going to do is you're going to create a flowchart in Google Classroom. You're going to use the file that I provide in there to start it off. What you're going to do is you're going to create a program that would get you blindfolded, or if you want to have a younger brother or younger sister or a parent you want to send through this trouble, feel free to do that too. Somewhere through your house, all right? So it could be like from your bedroom down the hallway to another bedroom. It could be, you know, to the bathroom to brush your teeth. Do whatever you want, all right? Make it fun, make it interesting for yourself instead of, you know, just a boring, go out the door and go down the hall. All right, we want to make something interesting. As part of this, include full details. Remember, when we're looking at this, it's going to be as, you know, well defined, all right? Think of it as if you're teaching a machine how to do this. You can't just say walk forward and then turn left because you didn't give it a time for how long it needed to walk forward. You didn't give it a distance. You didn't give it the amount of steps to go forward. You need to be very what's called explicit, very defined in what it needs to do. As part of this, I want you to also include a minimum of 2 different decisions, all right? Decisions that this robot has to make, and include at least 10 steps in there as well, all right? Remember, use these decisions, these if statements, when appropriate, and you need to be as exact, all right? You have to be very exact into what's going on there. And then once you're completed, you're going to submit it to Google Classroom, and anything you don't do is just going to be homework itself for tonight. So let's give you an example on how to do this itself. Oops, I got to sign back in. Let me sign back in here for a second. Next. Alrighty, so this is what you're going to see in your template right here. All right, you can zoom in, you can zoom out using this tool right here. So I'm going to zoom in, make things a little bigger. Okay, so we're going to go ahead. First thing, I'm going to say this is like how I wake up in the morning. So I'm going to do a flow chart for how to wake up. So first thing, start program. My first task that I'm going to need to do, I'm going to come up here and I'm going to draw the shape. And now you'll notice if I double click on this shape, I can actually type in there. So first thing is wake up. All right, and I'm getting up in the morning. All right, and I like to make them centered because I'm a little neurotic like that. All right, now I need to do an arrow to my next spot. And you notice I can go right in here and click, drag it down. All right, what's my next one going to be? And I want to make sure it's the same exact size too because I'm a bit neurotic. So I'm going to click on this and I can actually just Control-C, Control-V to copy it down. All right, so now they're all going to be the same size as I go through there. All right, so usually after I wake up, the first thing is, I can do one thing, check cell phone. Actually, usually it's turn off alarm. That's probably the first one, turn off alarm. All right, then lines goes down. And then usually I make a decision. Let's see, where is my decision? Here we go, flowchart decision. I go in here, I put this diamond. Alrighty, my decision after I turn off the alarm. Is it time to wake up? All right, that's my decision there. You notice it's not really fitting in there, so I'm gonna make it a little wider. That way it's looking a little nicer there. Is it time to wake up? So now I got to go ahead and I make 2 things. So first thing is if it's a yes, all right, so I bring my line down. I'm going to put in a little text there. All right, you'll notice the text box is right up here. And I'm going to go, yes, it is time to wake up. All right, or I'm going to do an arrow off to the side. I'm going to make a little line this way. Line. I'm going to bring that line up. All right, I'm going to pull off one of these here because if it is a no, all right, let's copy and paste that. We'll go no. Then what I need to do, whoops, didn't want the text box. I want to copy and paste this to make sure it's the same exact size. Copy, paste. So usually if it's not time to wake up, I'm going to go back to sleep. All right. And then I can continue on my line back up here. And you'll notice for me, I like to make them, and this is generally how flowcharts do go as well. You try to make them as straight up and down and left as right as possible. If I was to go ahead and here, let me do an example. Just do this. It starts to get ugly really fast and you start losing track of where things are going on there. Let me see if I can bring that back. Nope, I can't, but you guys get the general idea. So I would keep on going through this. Now for you guys, you are going to do this again as if someone is coming from one of your rooms in your house to another room in your house blindfolded. For this, obviously you're not going to be blindfolded, but you're going to go ahead and you're just going to test it out as much as you can to get this flowchart down. We are going to be testing this later on in the week, but don't do it quite yet because I want to make sure you guys do it in a safe way so no one gets hurt or stuff along those lines. because I don't want to get in trouble, and I don't want you guys to hurt yourselves either. All right, at this point, that's all I got for today. It was a long video today because I had to explain what's going on there, but catch you later.